Hello everyone, I'm Rislan Eshparti from Université Lyon 1 and in this presentation I'm going to talk to you about a new graph matching approach based on aggregated search and named LaSaS. So before we delve into the core of this presentation, let's talk about graphs in general. So graphs represent a widely used and efficient tool for modeling a broad range of problems and applications, such as social networks, and most of the real-life datasets are represented by networks of labeled entities. Also, querying graph datasets proves to be an important task in order to fully exploit the knowledge within these datasets. On the other hand, graph datasets are usually noisy, which makes the approximate graph matching tools and frameworks highly required and favored to alleviate restrictive query answering that is achieved by traditional and classical graph querying tools. In this presentation, we propose a new approximate graph matching approach named LaSaS. So here are the outlines of the presentation. First, we define and give the motivation of the aggregated graph search. Second, we discuss important related works. Then we present our proposed framework LaSaS, followed by the experimental evaluation to show its performance under different parameter settings and also to compare it to related works. And finally, we give a conclusion in section 5. Aggregated graph search problem, definition and motivation. In this part of the presentation, we will define the aggregated graph search problem in a trivial way and in a formal form. Then we will outline the motivation of the aggregated graph search. Trivial definition. Let Q be a graph that represents the user query, and let B be a set of graphs or fragments that are not isomorphic to Q. As depicted in the following figure, the aggregated graph search consists in finding a matching between Q and an aggregation or a combination of fragments in B. In other words, aggregated graph search aims at building a match to the query from substructures or fragments of several different graphs. Formal definition. Let us consider the following elements. Query Q. The query Q is an undirected labeled graph that represents the user query. Target graphs. Target graphs are represented by the set P of P graphs, which are referred to as fragments. And fragments are also undirected labeled graphs. The answer set A. The expected answer set A is a group of K aggregates denoted by AI. And an aggregate is the union of several fragments from B such that the aggregate is constituted by as few fragments as possible. The matching eta. Eta denotes the matching that associates the aggregates in the answer set A to the query. C is the objective function to optimize when looking for a matching. And the matching is said optimal when the objective function C is equals 1. Finally, we define the aggregated graph search problem. Given a set of fragments B, a query Q. The aggregated graph search problem consists in finding the matching eta that associates the answer set A of K aggregates to Q, the query, such that the objective function C of the matching eta equals 1. The problem of aggregated graph search problem was proved by us to be NP-hard. Motivation. The motivation of aggregated graph search problem is twofold. First, the aggregated graph search enables finding additional answers to a query where a classical graph search method such as graph isomorphism can't find any. Second, the aggregated graph search performs a low granularity search on graphs and enables finding a matching between a query and several scattered graph structures. Related work. The graph querying is a crucial task as most of the actual graph datasets are being stored and exploited as graphs, and many graph querying techniques exist in the literature, and the proposed framework is closely related to aggregated search and approximate subgraph matching. So in this part of the presentation, we provide a brief description of the graph querying methods that are based on subgraph matching and the aggregated search in graphs. So for the subgraph matching, subgraph matching is a well-studied problem with a rich literature, and two main categories fall under the subgraph matching problem: the exact and the inexact subgraph matching. So for the exact subgraph matching, it finds exact answers to the query via graph isomorphism, and approaches in this group are criticized for their attractability, their cost-prohibitive characteristic, and they are also restrictive with regards to the number of answers to the query. On the other hand, for the inexact graph matching, it allows slight differences between the query and the matches, which is highly suitable for actual needs as graph datasets are usually noisy, and also relevant answers could be found using approximate matching. And under this category of inexact subgraph matching, we find subgraph matching based on graph simulation, which can be determined in quadratic time and is defined by a relation between the query nodes and the target nodes. However, it suffers a considerable loss of structural similarity, which makes it untailored for many applications such as in bioinformatics. Another variant of inexact graph matching is the graph homomorphism, and the idea here is to find mappings to the query such that node labels difference falls under a threshold, whereas the query edges are mapped to paths of a given length. And more related to our work, Tian and all the other authors proposed a tool called SEKE, and the approach allows approximate matching by breaking the query into subgraphs and finding small hits that are assembled to form a match. And although SEKE method is based on an efficient indexing to speed up the processing, it actually reduces to solving the maximum click problem, which represents a costly operation. And although not pursued here, approximate and inexact subgraph matching encompasses decades of research work, so we can't give an exhaustive list about all related work in this area. Aggregated search in graph databases. Aggregated search is in fact a familiar search paradigm in information retrieval in the context of documents. However, few works tackle the problem of aggregated search in graph databases. Ergazel and the other authors studied the problem of aggregated search in labeled graphs, and their problem formulation is close to ours. Nevertheless, their method looks for exact matches, which is restrictive on one hand, and on the other hand very expensive due to the maximum common subgraph search and the maximum click detection, which are considered as being among the most expensive operations on graphs. In this part of the presentation, we present our query processing algorithm named LaSaS, which is a heuristic solution intended to solve the problem of aggregated graph search. We expose the proposed algorithm and its different steps. The LaSaS algorithm works in three distinct steps. First, the selection step that aims to select the most relevant fragments from the fragment set B. And second, the aggregation step that combines the relevant fragments found by the selection step to form the aggregate. And third, the refinement step that enhances the quality of the aggregate by pruning irrelevant nodes and by mapping paths of a thresholded length to unmapped edges, if any. So let's begin with the selection step. It's the first step that consists in selecting the most relevant fragments, as many as necessary to cover the whole query queue. The selection is based on successive iterations of two main substeps. First, the similarity checking, and two, the query updating until a stopping condition is verified. In the similarity checking, a rank is associated to each fragment in B, which is given by a similarity metric denoted by S. And we will not detail the similarity metric in this presentation. However, it is worth mentioning that it takes into account the label similarity of nodes and the structure similarity between the query and the fragment. And for the query update substep, the foremost role of it is to ensure complementarity among selected fragments. This step updates the query by removing nodes that are covered by the selected fragment, thus enabling subsequent selections to choose fragments covering complementary parts of the query. And this can be achieved in two ways: by using the maximum common subgraphs, and we first compute the maximum common subgraphs of the query queue and the selected fragment, and then this common subgraph is withdrawn from the query queue while keeping the boundary nodes that belong to the common subgraphs. And the other way to update the query is by using a wait update routine, that is to alleviate the complexity cost of computing the maximum common subgraphs by performing just a wait update on the query, such that removable nodes on the query will be weighted by 0 and by 1 otherwise. In the aggregation step, the fragments obtained upon successful completion of the selection step are stored in the solution set denoted by S, and the aggregation step constructs an aggregate A from the solution set such that the vertex set of the aggregate is the union of all the vertex sets of the selected fragments, and the edge set of the aggregate is the union of the edge sets of all selected fragments. The refinement step. The refinement step of an aggregate is achieved by either connecting the aggregate whenever it is disconnected or by pruning irrelevant nodes from it. So, cases when the aggregate is disconnected may occur when selected fragments cover disjoint areas of the query, leaving some query edges unmapped, and our algorithm maps these edges to paths by performing a path search in B in order to interconnect the connected components in the aggregate. And to this end, we perform a search of a path between any two nodes belonging to different connected components of the aggregate in the graph G, which is the union of all the fragments in the B set. To this end, we customize the Dijkstra algorithm by adding a constraint threshold in the path length, where only paths having a relatively small length are considered in order to speed up the search time, as long path search will be abandoned once the threshold exceeded, and on the other hand to preserve semantic relevance within the aggregate. And finally, the path search stops once the aggregates become connected. And for the pruning, the aggregate is refined by withdrawing irrelevant nodes, and to do so we iteratively prune irrelevant leaves from the aggregate until no irrelevant leaf is left, where a leaf is a vertex with a degree equal to 1. And as depicted in the figure, not all irrelevant nodes are pruned from the aggregate by the end of the pruning process, and however, by limiting the pruning to irrelevant leaves, the connectivity of the aggregate is preserved, as the removal of an irrelevant node with a degree that is greater than 1 may disconnect the aggregate. Experimental evaluation. In this part of the presentation, we show the empirical evaluation of the proposed approach. We first describe the experimental setup along with the graph datasets and the evaluation methodology. Then we present the evaluation metrics used. Second, we present and discuss the obtained results. Experimental setup. Graph dataset. In order to evaluate our method, we use the real-life datasets DBpedia knowledge base that consists of RDF triples extracted from Wikipedia. We considered a large number of triples from 10 different entities. Fragments generation. In order to constitute the set of fragments B, we partition the dataset used in such a way that no fragment is isomorphic to the query Q, and to avoid crossing edges between fragments, nodes belonging to the crossing edges are duplicated in the fragments involved. Query generation. Two parameters are necessary to generate a query: the number of nodes denoted by n and the query diameter d, which represents the largest distance between any two nodes. A query is generated by extracting a subgraph from the dataset and introducing some label and structure noise to it. The label noise is generated by randomly modifying some words in the original label, while the structure noise is provided by randomly removing or adding some edges. Evaluation metrics. The F1 measure is used as the main evaluation metric to show the effectiveness of our method. It combines the recall and precision. And in addition to the F1 measure, the runtime is also reported. Methodology. Our experiments are based on the following guidelines. We create 4 query sets and we generate 100 queries under each set. First, we assess the influence of the structural noise on our method by fixing the label noise and varying the structural noise for all the 4 query sets. Similarly, to assess the label noise influence on our method, we fix the structural noise and vary the label noise on all the 4 query sets. We vary the ratio of the matching nodes in the query, that is, the query nodes that are surely present in the fragment set B, and see the repercussion on the performances of our method. Last but not least, we compare LaSaS to state-of-the-art tools, SEKE and Blinks, which is a keyword graph search method. Finally, all algorithms have been implemented in C++ and all experiments were performed on a single machine with 16 GB of main memory. Label noise influence. We vary the label noise and report the F1 measure in figure A. Having the structural noise fixed to 10%, the F1 measure does not reach 1 when label noise equals 0%. Results show that LaSaS maintains the same performances for 0 to 10% of label noise, meaning that it efficiently discovers the correct matches despite the noise. However, when the label noise goes up to 30%, F1 measure drops considerably, which shows that LaSaS is label noise sensitive. In figure B, we show the runtime for all query sets while varying the label noise. Results show that for each query set, the runtime is even for different values of label noise. However, a slight increase of the runtime is noticed when the label noise reaches 30%, which is normal as the method spends additional time to look for other candidate matches. Altogether, increasing the label noise does not incur a considerable computational cost. Structural noise influence. Figure A reports results for different values of structural noise while label noise was set to 10%. When no structural noise is added, the F1 measure does not attain 1 due to the label noise being set to 10%. Moreover, the F1 measure does not have an abrupt variation for all query sets, with the lower bound being 0.8 and the upper bound being 0.86, which translates the capacity of LaSaS to find the correct matches despite the added noise on the structure. Figure B reports the runtime while we vary the structural noise, and the results show that the runtime is almost steady for all query sets. That is to mention that the computational cost incurred by the added structural noise is negligible. Ratio of query matching nodes. We refer to the ratio of matching nodes that are already in the fragment set B by phi, and we investigate its influence on the performances of LaSaS. Figure A reports the F1 measure and shows that performances are optimal when the ratio of the matched nodes is equal to 100%, and it decreases gradually when the ratio of the matched nodes decreases. This shows the effectiveness of our method as it finds the best results when they are available. The reported runtime, as shown in Figure B, increases with the ratio phi, which means that the method takes more time to process as there are additional relevant answers in the B set. LaSaS versus Saga and Blinks. In the following table, we compare our method LaSaS to two state-of-the-art tools, Saga and Blinks. Results in this table show that LaSaS outperforms both Saga and Blinks in effectiveness by achieving a greater F1 measure and in efficiency by finding results faster. Conclusion. We discussed a novel framework for approximate graph matching based on aggregated search called LaSaS. The proposed approach enables an effective graph querying without any knowledge of the schema of the data graph, and the framework joins ideas from aggregated search and graph matching to effectively find approximate matches for a query from a set of heterogeneous graphs. LaSaS, the proposed framework, is based on three key ideas. First, aggregated search strategy in order to enrich the set of answers, and second, a lightweight graph similarity metric that takes into account both the nodes label and structure and graph structure similarity to enable finding approximate matches, and finally a graph weight update that replaces the maximum common subgraph search task and reduces the complexity cost. Also, the empirical evaluation over the real-life DBpedia graph illustrates the effectiveness of our method over different parameter settings and incorporates the stability of LaSaS. Moreover, results indicate that the proposed method outperforms the state-of-the-art related approaches by finding more precise matches. Thank you everyone for your attention.